Hello everyone, and I hope you are fine. Welcome to a final lab of the session, lab number 11. In this lab, we are already quite familiar with MATLAB functions, and we have already been introduced to the MATLAB console framework in which we program and we put the amount of codes into the lines in the console or in the editor window, and we use that editor window to demonstrate us what the results are being presented on the command window. So that was the basic framework which is usually used for MATLAB, which we discussed in the previous lab. But in this lab, in lab 11, we are using some advanced MATLAB tools, which are quite fascinating and these are quite friendly and have graphical interface for academic purpose, so you can demonstrate multiple circuits and program them, and it has various amount of features, and I don't think it is quite possible that one can completely describe a Simulink tutorial into one session. So it's a very vast domain. I'm talking about the Simulink function of the MATLAB. So the Simulink is a sub program in a MATLAB. So it's basically created by MATLAB, but it's sort of a graphical interfaced MATLAB, and it has a lot of features, and it is a quite a progressive learning curve. So you might know a little bit in this session about the Simulink, and then you can explore it further till your final year, and you can explore various uh, amazing aspects of Simulink. So it's one of my favorite softwares, and I always prefer Simulink for any sort of simulation work. So yeah, let's get started. And what we are today trying to do is we are trying to um, plot our basic RLC circuit. So we are already quite familiar with the RLC circuit when R, L, and C, that is the resistor, inductor, and the capacitor, are in actually the series formation with the source, single phase source, right? So we are going to demonstrate a simple basic model, and I'll get you through the phase when we mutually go through the libraries and explore some functions, put up some sources, and a lot of details into that. So and then you can always feel free to explore more options and more uh, features in this function. So yeah, there is a lot of stuff to explore on you at your own end. So let's start with the basic ACRLC plot on Simulink, lab number 11. All right, so let's go to the traditional MATLAB window. So all right, so this is the traditional MATLAB window which we usually see, right? So this is usually referred to as the classical MATLAB, or you can say as the MATLAB console. So console is something which is regarded as a framework on which you code something, and then you have a result being displayed on the on some other window. Maybe it's a command window or some other demonstrative window, like different programming languages. So it's quite similar to the programming stuff, right? But now when we go to the graphical softwares, or the graphical interfaceable software of of MATLAB, which is Simulink, you can always find it at the top. And you can, when I drag the mouse over there, so it's already saying that start Simulink. So when I click this, all right, so it will start Simulink, and it will give me a lot of options. There are a lot of new libraries um, which are quite exciting to explore here, and I'm quite curious to let them know. But I know um, that you might face a little problem if I go too much into deeper to this aspect. But the purpose of saying all this is that there are a lot of features already built in programs, or already built in models, that you can always explore, and you do not have to build it from scratch. So it's a very rich in repository. So you can always find, like, you can have a blank subsystems, or you can create a library, or maybe you can have a generic code. So it's kind of a simulation based world in the MATLAB, which includes the graphical interface. Plus, you can also have a code integrated to that graphical unit. Plus, you can have maybe a GitHub repository affiliated to that. Maybe you have an SVM, maybe you have a machine learning and deep learning algorithm already placed there. So it's a very, very interesting world, and I must say that you need to spend some time over this. So we will start with the 101 course. So we'll start with the basic blank model. So we'll drag our mouse over the blank model and we'll create model. So it will take a little bit time. This is MATLAB 2021B, I think, 2019B, right? So it might take a little time if you have a slower PC. So be patient with that. So this is actually the basic blank model of Simulink. So it is quite similar to what was the console, right? So console was quite whitish framework with the top ribbon, and it is quite similar to that. But if you see at the top, very top, it says it's a Simulink file, right? So it's a Simulink file, and all of the options seems like they are familiarly as they are familiarly present in the console or the classical MATLAB, but they are not. They are quite a bit different. All right. So, so it's a blank model. Now we have to import like all the traditional graphical interfaceable units. What we have to do is we have to open the library and we have to import each of the component which we are trying to use in our software, in our circuit. So here's, if you go to the library browser, you open this function and you will have this thing. And now you can see there are a lot of different libraries which extends from audio toolbox to automated driving toolbox to fuzzy logic toolbox, reinforcement learning, deep learning, powertrain block sets, and whatever you can imagine, everything is there. So maybe if you are from electronics background or mechanical background, you can have everything here already in the mathematical framework. So you can always feel free to explore it. So number one thing is we want a source. So let us type without the library which we usually use for power simulation or circuit simulation is usually um, uh, power sim, right? Power PWER, power sim. So power sim is basically the library which is used for simulation of power, but usually in the traditional methods we used to go through the libraries and search out each of the components individually. But now we have the search toolbar, so I can just type it, whatever the component I want, and I can drag it into my windows. All right. So to find the AC single phase AC source, what you have to do is you have to go to Simscape into the library, and then you go for electrical section electrical, and then you go for specialized power systems. And whenever you pick any of this, any of the tool or any of the block from this specialized power system block, you have to import one thing, which is power GUI block. So I have, let me repeat it one more time. So what I'm saying is when you go through, maybe you go through electrical and you go to specialized power systems. So whenever you go to specialized power systems and you go to, let's say, fundamental blocks, and in the fundamental blocks you go for electrical sources and you import this AC voltage source, right? So AC voltage source came here, right? All right. So you see, I have imported a block from specialized power system toolbox, which is AC voltage source. So whenever I pick any component from a specialized power system block, there is one thing which we have to do it every time we select a component from the specialized power system block, which is in the fundamental blocks we have to import this power GUI platform, right? So what does is actually this is a GUI engagement platform which has a real-time simulation statistics for power systems, and we might not go into quite a bit in detail about how it works, but it's quite a fascinating idea. So always remember when you're importing these, if any time you go through Simulink and you have to import at least one thing from this power specialized toolbox, maybe you select an element or a measurement toolbox or a power electronics, anything from this power specialized power system block, you have to import this power GUI block. Otherwise, this thing won't work, right? So the first thing that I required was the single phase source, which I actually dragged from electrical sources, dragged it from here to the main screen, and then I'll go for the loads maybe. So I want an RLC element, right? So let us go to elements, and in elements I'll have a series RLC branch. All right, that's great. So if I import this, all right, so now I have a RLC branch, and you can see it when I double click on this branch. All right, so it gives me a resistance and inductance and capacitance. So if I wanted to convert this into a resistor, maybe I can type the inductance and capacitance is 0. Now it becomes a pure resistor. You can select it from the branch menu, and maybe you can select an abrupt value, let's say maybe 6 ohm resistor, apply it, and maybe you can have a resistor here, right? So it's quite fascinating to have this resistor. You can convert the RLC branch and remove that C and L element and convert it into a resistor. Another option is to flip it in case if I wanted to have a understandable connection and can be demonstratable. So I wanted to convert into vertical structure. I'll copy it, I'll paste this structure, I'll copy it, I'll paste it again, and this time I want it to be not a resistor but an inductor, maybe some let's say some random value, exponential -4. We usually pick a inductance value lower due to the obvious reasons. And yeah, so what are the reasons why we need a low inductance? Usually for power systems we have a high inductance, but usually in circuits a small amount of inductances are present because the length of the wire is not so much in the smaller circuits. So that's why we do not have usually too much inductance in the small circuits unless we are talking about huge transmission lines, right? So always remember that. So when we are, if you somehow in the future go to model a transmission line which is kilometers long, so you would see that this inductance value is quite high. So usually we initialize with a very low value. Last thing is we want to have a capacitor with still have a smaller value, let's say 12. So I'm just picking random values, -4. All right, so we have an RLC series circuit. Let's connect these terminals. All right, and let's connect this with the source. All right, so let's move this block here. Maybe it looks a little bit less crazy. All right, so all right, so we have a source and we have an RLC circuit. Now the problem is that we do not have any measurement tools available here, so we need to import some measurement tools. So number one thing that we need to import is actually your measurement tools. So let's go for current measurements. All right, so it's like an current measurement is like an ammeter, and another one could be voltage. Oh, sorry, this would be your voltage measurement. All right, so this is your voltage measurement, so I'll drag it out. Okay, so now you can see this is the current measurement, so it will be in the series. So I will remove this branch, connect this to the source and the negative terminal back to, so this is like an ammeter connected in series with the main circuit. And for measuring the individual voltages across each resistor, right, I want 3 different voltage measuring units. So I'll copy it, paste it, copy it. Oh, what's that? All right, so I'll just join it like across the resistor, okay, across the inductor, and then across the capacitor. All right, so we have voltages for all of the three components, and of course if they are in series, the current from each of the element would be the same as measured by this current measuring device, right? So fair enough. All right, so what's the point, what we are trying to observe here? Actually we are trying, what we are trying to do, what is the goal of this lab actually? Yeah, we didn't discuss it at quite, and which is quite important actually. So what we are trying to do is to, we want to show these values of voltages and current on a, in the form, in the waveform format, right? So we want the voltage and current waveforms in a scope, right? So we want a graph, sort of graph in which the voltages waves are plotted and current waves are plotted, and we can compare it. So we can observe that what happens to the voltage and current when it's passing through the resistor, when it's passing through the inductor, and when it's passing through the capacitor. And I think we have a quite bit idea if we are familiar with the theoretical backgrounds of it. So let's explore it manually, and then we can always go through it. But the problem with these measurements, voltage measurements and current measurements, is that it is unable to show us in the form of graphs. To display values in terms of graph, we need another component which is called scope. The scope is a device like an oscilloscope, right? So that's why it's also called a scope. It's exactly like a oscilloscope, and we want to display that. So let us go into the scope first. All right, let's double click on the scope. So this is the sort of the scope which we might see when we double click on it, but the problem is there is only one input here. So let's go to file, number of inputs, and let's select it to 2. So now it has 2 inputs. Let's connect one to the current and one to the voltage. So now what is going to happen is this scope will show us the voltages of this resistor and the current flowing through this resistor. That's cool, right? And we have to do this for the inductor and capacitor. So I'll copy it, paste it, copy it, and paste it. So I'll connect that to the current. All right, so we want the same current because the same current is flowing through the RLC. So the current values will be the same for all of them. However, the voltage would be different, of course. So I'll drag the voltage from here. All right, we're done with this. Now, what we usually do is we do not want, all right, let's start it, let it simulate. And we have initialized the values of RLC with 6 ohm resistor, 100, or maybe like 10 milli Henry sort of, and like 1.2 milli farad. All right, so but we didn't initialize the value of voltage, so let us take the regular voltage, which is 220, and we'll multiply with square root of 2. And I think you might not feel any confusion why I have like multiplied with square root 2, right? So yeah, I can ask it in the why in the Viva that why I multiplied this with square root 2. If you are familiar with the last lab, I think it's not a bit difficulty in understanding what I'm talking about. So it's actually the peak amplitude, right? Okay, so now I actually solved your problem, right? So always go to check back that formula that we studied in the last lab, and you can always find that answer, right? All right, so and I initialized all the values, and let's run this. So in the green button, when you play this green button, it gets run, and this says this going to be run for 10 seconds. 10 seconds is quite a lot time, and you can see that if I run on 10 seconds, it will compile. And when you turn on the scope, you can see, oh, this is a very populated signal. So I do not want a very populated signal compressed into the shield, and I want a precise part of the signal. Let's say maybe I can say for 0.1 second, a small signal, so I can have a sufficient amount of waves so that I can actually look back and compare it, right? So actually what my purpose is actually to look at the wave and compare it with the current and voltage form. So if it's too squeezy, I cannot see into it, right? So let's take it for very small time, that is 0.1 seconds, and now I'll check the scope. All right, that's fair enough. All right, so there are two problems here. That is, the current and voltages are on actually the same graph. So I can do with this, actually I can go with view, layout, and I can select two boxes that will split current and voltages into two individual matrices, right? Individual forms, right? So now the current is separated from the voltage, and obviously it's easy to observe that. Similarly, I'll apply that for the rest of the two. Layout, I'll have two individuals, and similarly I'll have a layout and I'll have two individuals. Or maybe you can say that both of them are yellow. I don't like the yellow one. Maybe I wanted to change the other one into red. So maybe you can go into the styles, and the active display one, you can turn it into red, apply that. All right, so this is in red, and you can do this for the rest of them. Go for it, make it red. All right, so you can have a fine line distinction between what's going on, right? All right, so let's do this for the last wave. All right, style, and let's make it red. So the part one problem is solved, that the current and voltages are splitted, fair enough, and they have different colors. So I think I can fairly distinguish between. But the problem is the wave is quite strange and quite pointy, sort of some kid has drawn this wave and he's not so precise with that. So this is actually happening because of the compiler, right? So what is a compiler? When you run a simulation, there is a compiler which has a different precision level. So if we want a very smooth wave, so we want a high caliber uh, compiler for it. So we have to change the compiler. How to change a compiler? You go to the modeling, go into this gear button, and then what you're going to do is you select not automatic but ODE45 dormant prints. For ODE45 is the highest level uh, solver, or you can say the compiler, right? So ODE5 means ordinary differential equations. It can solve 45th order differential equations, so it has a higher accuracy. Further, you can also go to the maximum step size and you can mark it E minus 3 maybe. You can apply it, and I expect that it it should have a different result right now. there. All right, so you have this wave, beautiful wave, right? So you can see that one of the each of them are partially apart. Then in the case of resistor, it's quite exactly the in phase with the current, and when it's inductive, it's actually leading voltage is actually leading the current, and when it's capacitive, it's actually lagging behind with respect to the waveform of the current. So this is actually what you're going to examine in this lab, and that's it. And it's quite easy to play with this thing, right? So you can always go through this. So this is actually the example for uh, single phase circuit, right? So you can always feel free and go to the libraries and check out some more beautiful functions, such as you can go to the electrical libraries and you can go for maybe elements. And in elements, if you can see, there are three phase, right? So three phase RLC branches. So you can also make this circuit on three phase. So always try to do something that is like quite unique, and you can implement this on three phase system. Of course, if you can see, if I import this here, so in three phase RLC branch, there would be three different phases, not like this one. There would be three different phases coming to this, and of course for that you have to import not single phase source, but you have to import a three phase source. That's also available in the library. So in the lab number 12, which is our next lab, uh, you have to actually go for the star delta circuit. So you can also make this star delta circuits using maybe these elements, right? Imported them individually, or if you can find a block into the library, that's perfectly fine, right? So that's an open-ended lab, and that you have to explore it yourself. I'll further guide you on that in some other video. All right, and that's for the lab number 12, and this is the end of lab number 11. To summarize it all before I close this lecture, um, what we learned in this lab, actually we learned to simulate a single phase circuit, single phase RLC circuit into Simulink MATLAB, which is a graphical interfaceable unit of MATLAB. And in that, when we compared the voltages and currents of our resistor, inductor, and capacitor, we found out, or we can say we verified actually how the current and voltages behave with respect to these elements, such that the voltage and current remains in phase for resistor, but for inductor, the voltage actually leads the the current, and for the case of capacitor, uh, the current leads the voltage, right? So we actually verified that experimentally. So whatever you study in your course, you can always plot it here. Feel free to explore further options. So it's quite good with AC analysis. So that's it for today's lab number 11, and see you in the another